The night of March 15, 2024, began like any other at the Catalina Sky Survey in Arizona. Astronomer Dr. Sarah Chen was reviewing the automated detection alerts from the previous night's observations when an unusual data point caught her attention. A faint smudge of light, barely visible against the background stars, was moving with a trajectory that didn't match any known object in our solar system. What she didn't know at that moment was that she had just discovered humanity's third confirmed interstellar visitor, an ancient comet that would soon be designated 3I Atlas. The discovery sent ripples through the astronomical community within hours. Unlike the rushed observations of Oumuamua in 2017, which was already leaving our solar system when discovered, or the relatively brief visit of Comet Borisov in 2019, this new interstellar object was detected while still in the outer reaches of our solar system, giving scientists an unprecedented opportunity for detailed study. Dr. Chen recalls that pivotal moment. The orbital calculations kept giving us the same result, an eccentricity greater than 1. In simple terms, this object was moving too fast to be gravitationally bound to our Sun. It had to have come from interstellar space. The preliminary orbit suggested the object originated from the direction of the constellation Lyra, though its actual journey likely began millions or even billions of years ago. Within days of the discovery, telescopes around the world swiveled to observe the new visitor. The Hubble Space Telescope captured the first detailed images, revealing a classic cometary appearance with a distinct coma already forming despite the object's considerable distance from the Sun. Spectroscopic analysis began immediately, with teams racing to determine the comet's composition. Before solar radiation could significantly alter its surface, the early data was fascinating. Unlike our solar system's comets, which typically show strong signatures of water ice, 3I Atlas displayed an unusual abundance of carbon monoxide and molecular nitrogen volatiles that would have been depleted in any comet that had made multiple passes close to a star. This pristine composition suggested the comet had been preserved in the deep freeze of interstellar space since its formation. Around another star system, Dr. Michael Rodriguez, lead researcher at the European Southern Observatory, published the first comprehensive analysis in late March 2024. What we're seeing is essentially a time capsule from another solar system. The isotopic ratios we're measuring are subtly different from anything in our solar system, confirming beyond doubt that this object formed around another star. The naming process followed established protocols. The International Astronomical Union designated it 3I Atlas, the 3I, indicating it as the third confirmed interstellar object, and Atlas honoring the asteroid terrestrial impact last alert system that had independently confirmed the discovery. But beyond the technical designation, the comet quickly captured public imagination as news outlets worldwide reported on our latest cosmic visitor. By April 2024, as 3I Atlas crossed the orbit of Neptune, something unexpected happened. The comet began brightening faster than models predicted. Dr. Lisa Park from NASA's Jet Propulsion Laboratory explained in a press conference, "We're seeing outgassing activity at distances where most solar system comets would still be completely dormant. This suggests a composition rich in supervolatile substances that sublimate at extremely low temperatures." The enhanced activity made 3I Atlas an even more attractive target for study. The European Space Agency fast-tracked a mission proposal to send a probe to intercept the comet, though the extreme velocity of the object made such a mission technically challenging. Meanwhile, ground-based observatories implemented round-the-clock monitoring programs. As spring turned to summer in 2024, 3I Atlas continued its inward plunge. Each week brought new discoveries. The comet's nucleus was estimated to be between 5 and 8 kilometers in diameter, larger than Borisov, but smaller than the enigmatic Oumuamua. Higher-resolution imaging revealed an elongated, potato-shaped nucleus, tumbling in a complex rotation pattern with a period of approximately 15 hours. The comet's spectrum revealed a chemical treasure trove. Besides the expected ices, astronomers detected complex organic molecules, including methanol, formaldehyde, and even hints of amino acid precursors. Dr. Yuki Tanaka from the Japanese Space Agency commented, "We're essentially looking at the building blocks of life that formed in a completely different stellar environment. The implications for astrobiology are profound." Public interest soared as 3I Atlas became visible to amateur astronomers with modest telescopes. Online forums buzzed with observations and photographs. The comet's distinctive greenish hue, caused by diatomic carbon in its coma, made it easily distinguishable from background stars. Sky and Telescope magazine featured 3I Atlas on its cover with the headline, "Messenger from Another Star." By September 2024, as the comet crossed Mars' orbit, its tail had grown to spectacular proportions. Solar-wind interaction created a classic ion tail, stretching millions of kilometers, while a separate dust tail curved gracefully along the comet's orbital path. Professional astronomers used this opportunity to study how interstellar dust particles behaved differently from their solar system counterparts. The scientific papers published during this period read like dispatches from the frontier of knowledge. One particularly intriguing finding came from radio observations. The Arecibo Observatory's successor, the 500-meter aperture spherical telescope in China, detected unusual radio emissions from the comet. While not signals of artificial origin, as some sensationalists claimed, these emissions suggested unique plasma interactions in the comet's environment. Dr. Robert Anderson from MIT published a groundbreaking paper in Nature. The magnetic field measurements around 3I Atlas indicate it's carrying a fossil field from its original stellar system. This is the first time we've been able to study the magnetic environment of another star system, albeit indirectly. As 2024 drew to a close, 3I Atlas was approaching its closest point to the Sun, known as perihelion. Models predicted it would pass within 0.8 astronomical units of our star closer than Earth, but outside Venus's orbit. This relatively close approach meant the comet would experience intense solar heating, promising spectacular activity. The new year 2025 brought unexpected developments. Solar astronomers monitoring the Sun noticed increased activity in several active regions. The current solar cycle 25, was approaching its maximum, meaning more frequent and powerful solar storms. Dr. Jennifer Walsh from the Solar Dynamics Observatory warned, "We're seeing conditions that could produce significant coronal mass ejections. Any of these could potentially interact with the comet's trajectory." This possibility excited planetary scientists. While comets occasionally experience solar storms, the chance to observe an interstellar comet with its unique composition and pristine nature encountering ACME was unprecedented. Emergency observation plans were drawn up, and space weather forecasters began providing daily updates on solar activity. In mid-January 2025, the scenario scientists had hoped for began to materialize. A massive filament on the Sun's surface showed signs of instability. Solar observatories watched as magnetic field lines twisted and strained. Dr. Carlos Mendez from the Space Weather Prediction Center issued an alert. "We're monitoring a significant magnetic structure that could produce a major CME within the next 48 to 72 hours. Given the current positions, any eruption from this region could potentially intersect with Comet 3I Atlas." The astronomical community held its collective breath. The possibility of witnessing an interstellar comet being struck by a coronal mass ejection represented a once-in-a-lifetime opportunity. Graduate students postponed vacations, telescope time was reshuffled, and space agencies prepared their instruments for what could be one of the most significant astronomical events of the decade. As January progressed, 3I Atlas continued to brighten. Naked eye visibility was predicted for early February, potentially making it the first interstellar object visible without optical aid. Amateur astronomers in the southern hemisphere reported spectacular pre-dawn views, with the comet's tail stretching across a significant portion of the sky. The stage was set for an extraordinary cosmic encounter. An ancient voyager from another star system, carrying secrets from across the galaxy, was about to meet one of our Sun's most powerful phenomena. The scientific instruments were ready. The world was watching, and the cosmos was about to provide a spectacular show that would advance our understanding of both interstellar objects and solar dynamics. The latest updates from observatories worldwide confirmed that 3I Atlas was maintaining its trajectory while showing increasing activity. Massive jets of gas erupted from its nucleus as ancient ices that had remained frozen for eons finally felt the warmth of a star. But this gentle warming was nothing compared to what was coming. In the turbulent atmosphere of our sun, forces were building that would soon unleash a storm of unimaginable power directly into the path of our interstellar visitor. Part 2. The Solar Storm awakens a cosmic collision in the morning of January 28, 2025, marked a turning point in this cosmic drama. At the Solar Dynamics Observatory, Dr. Jennifer Walsh stared at her monitors in amazement as the sun's photosphere began to show unmistakable signs of a major eruption brewing. The active region, designated AR3547, had been growing for days, its magnetic field lines becoming increasingly twisted and unstable. Now, the telltale signs of an imminent coronal mass ejection were impossible to ignore. "We're looking at a configuration that's textbook pre-eruption," Dr. Walsh reported to her team. "The magnetic field strength has exceeded 3,000 Gauss, and we're seeing significant shearing motion along the neutral line. This is going to be big." The timing couldn't have been more extraordinary. Comet 3I Atlas was currently positioned at 0.85 astronomical units from the Sun, placing it directly in the potential path of any CME originating from AR3547. Solar physicists quickly calculated trajectories and probabilities, their excitement growing with each confirmation that this could indeed result in a direct hit at the European Space Agency's Space Weather Coordination Center. Emergency meetings were called. Dr. Herman Opgenorth, head of the Space Weather Division, addressed his team. "We need to alert every observatory capable of observing this event. If our calculations are correct, we're about to witness something that's never been documented before: major CME impacting an interstellar comet." The solar physics community had long studied how CMEs affected solar system comets. The famous encounter between Comet Inc. and Acme in 2007 had provided valuable data, as had several other observed interactions, but those involved comets that had been repeatedly processed by solar radiation over millions of years. 3I Atlas, with its pristine interstellar composition, promised to react in ways that could only be theorized until now. By January 29th, the signs were unmistakable. The Solar and Heliospheric Observatory, SOHO, captured dramatic images of plasma rising above the Sun's limb, held in place by invisible magnetic forces. The structure resembled a cosmic arch, growing larger and more unstable with each passing hour. Space weather models suggested that when this structure finally erupted, it would produce a CME with speeds exceeding 2,500 kilometers per second. Dr. Madhulika Guhatakot, a senior NASA heliophysicist, explained the phenomenon to assembled press. "What we're witnessing is essentially a magnetic pressure cooker. The energy stored in these twisted field lines is equivalent to billions of hydrogen bombs. When they finally snap and reconfigure, all that energy will be released in a massive explosion that will hurl billions of tons of solar material into space." The comet, meanwhile, continued its spectacular show. Latest observations from the Atacama Large Millimeter Array in Chile revealed unprecedented detail about the object's composition. Dr. Stephanie Millam from NASA's Goddard Space Flight Center published urgent findings. "We're detecting molecular species that shouldn't exist in such abundance if this comet had ever been close to a star before. Molecules like methane and ammonia are present in ratios that suggest formation in an extremely cold environment, possibly in a molecular cloud before it even had a parent star." Amateur astronomers worldwide were now tracking 3I Atlas nightly. Social media buzzed with spectacular images showing the comet's distinctive dual-tail structure. The ion tail, glowing blue from carbon monoxide ions, stretched straight away from the Sun, while the yellowish dust tail curved along the comet's orbital path. Brightness estimates suggested the comet had reached magnitude 3.5. easily visible to the naked eye from dark sky locations. On January 30th, at 14:23 UTC, the inevitable happened. AR 3547 erupted in one of the most powerful solar flares of solar cycle XX-class. The X-class flare was accompanied by a massive coronal mass ejection, just as predicted. The SOHO coronagraphs watched as a halo CME expanded outward from the Sun, its Earth-directed component, confirming that the ejection was aimed almost directly along the Sun-Earth line and directly toward Comet 3I Atlas. The numbers were staggering. Initial estimates suggested the CME contained approximately 10 billion tons of solar material, traveling at speeds approaching 3,000 kilometers per second. The embedded magnetic field strength was measured at over 50 nsTesla, making this one of the strongest CMEs observed in years. At these speeds, the plasma cloud would reach the comet in approximately 18 hours. Dr. Nat Gopalswamy from NASA's Goddard Space Flight Center coordinated the global observation campaign. We've activated every available asset: the Solar Terrestrial Relations Observatory, Parker Solar Probe data, ground-based solar telescopes, and a fleet of instruments trained on the comet. This is a once-in-a-generation opportunity to study space weather effects on a pristine interstellar object. As news of the impending collision spread, public interest exploded. Major news networks began continuous coverage, bringing in expert commentators to explain the significance. The hashtag #CometVs CME began trending globally, with millions following updates in planetariums scheduled special viewing events, and astronomy clubs organized watch parties. The scientific community worked feverishly to prepare. Dr. Carl Battams from the Naval Research Laboratory, an expert on sun-grazing comets, offered predictions based on our models. The CME impact could trigger massive fragmentation of the nucleus. We might see the comet break into multiple pieces, each becoming a comet in its own right. Or, if the nucleus is more cohesive than we expect, we could see explosive outgassing that could brighten the comet by several magnitudes. Computer models ran continuously, each trying to predict different aspects of the encounter. Some focused on the plasma interactions, predicting spectacular auroral displays in the comet's coma. Others modeled the thermal shock, calculating how deep the CME's energy would penetrate into the nucleus. Still others examined the possibility of electromagnetic phenomena, including radio emissions and magnetic field reconfigurations. Dr. Geraint Jones from University College London's Mullard Space Science Laboratory had spent years studying comet-solar wind interactions. He offered a sobering perspective. What makes this event unique isn't just the pristine nature of the comet, but the geometry of the encounter. The CME will hit the comet almost head-on, maximizing the energy transfer. We could see excavation of material from meters or even tens of meters deep in the nucleus. As the CME raced outward, space weather satellites provided continuous updates. The Advanced Composition Explorer, ACE spacecraft, positioned at the L1 Lagrange point between Earth and the Sun, would provide crucial measurements of the CME's properties before it reached the comet. These measurements would help scientists understand exactly what was about to hit 3I Atlas. On January 31st, with the CME just hours away from impact, observatories worldwide were on high alert. The comet itself seemed to sense the approaching storm. Enhanced activity was reported, with new jets appearing on the sunward side of the nucleus. Spectroscopic observations revealed rapid changes in the coma's composition as different ices sublimated in response to increasing solar radiation. Dr. Casey Lease from the Johns Hopkins University Applied Physics Laboratory, who had studied numerous comet-CME interactions, provided context. What we're about to witness is essentially a cosmic excavation. The CME will act like a high-pressure hose, blowing away the outer layers of the comet and exposing material that's been locked away since before our sun was born. The scientific value of this event cannot be overstated. European Southern Observatory's Very Large Telescope in Chile was providing near-continuous monitoring. Dr. Colin Snodgrass from the University of Edinburgh reported, "We're seeing rapid morphological changes in the coma structure. It's as if the comet knows what's coming." The plasma environment around the nucleus is becoming increasingly turbulent. Space agencies issued alerts to satellite operators, warning of potential impacts when the CME reached Earth a day after hitting the comet. But for now, all attention was focused on the impending collision. Scientists prepared their instruments for rapid cadence observations. Knowing that the most dramatic effects might last only minutes or hours, public engagement reached fever pitch. Science museums extended their hours, offering telescope viewing and expert presentations. Online streaming platforms reported record numbers of viewers tuning in to watch live feeds from professional observatories. The event was being called the astronomical event of the decade by media outlets worldwide. Dr. Amy Simon from NASA's Planetary Sciences Division summed up the moment. "We stand at the threshold of an unprecedented observation. In the next few hours, we'll watch as material from our Sun collides with material from another star system. The data we collect will revolutionize our understanding of both solar physics and interstellar objects. This is why we do science for moments like these, when the universe provides us with a natural experiment of cosmic proportions." As the final hours ticked down, last-minute adjustments were made to observation plans. High-speed cameras were synchronized, spectrographs were calibrated, and data storage systems were cleared to handle the flood of information about to arrive. The stage was set for one of the most spectacular celestial events in recorded history. The latest models suggested impact would occur at 8:47 UTC on February 1, 2025. As that moment approached, millions of eyes turned skyward, and hundreds of instruments stood ready. The ancient ice and dust of an interstellar wanderer was about to meet the fierce power of our star in a collision that would echo across the scientific literature for decades to come. Part 3. Impact. When interstellar ice meets solar FUR, February 1, 2025. 8 o'clock UTC. The world held its breath as the final countdown began. In control rooms from Hawaii to Chile, from the Canary Islands to Australia, astronomers sat poised at their instruments. The coronal mass ejection, now 47 minutes from impact, raced through space as an invisible tsunami of superheated plasma and twisted magnetic fields. Comet 3I, Atlas, unaware of its impending fate, continued its ancient journey. Its icy nucleus, sublimating peacefully in the morning light of an alien sun. Dr. Maria Gonzalez at the Keck Observatory in Hawaii made final adjustments to the adaptive optics system. All systems nominal. We're recording at 1,000 frames per second in multiple wavelengths. If the nucleus fragments, we'll catch every piece. Her team had been awake for 36 hours straight, fueled by coffee and the excitement of witnessing history. At 8:15 UTC, the first indirect signs of the approaching CME became visible. The comet's ion tail, usually flowing straight away from the sun like a cosmic wind, began to show perturbations. Dr. Geraint Jones, monitoring from the European Space Agency, noted, "We're seeing the tail starting to waggle. The magnetic field preceding the CME is already interacting with the charged particles in the tail. It's beginning." The Solar Dynamics Observatory captured the CME's current position, its instruments tracking the billion-ton cloud of plasma as it bore down on the comet. The numbers were staggering. Temperature exceeding 2 million Kelvin. Velocity holding steady at 2,847 kilometers per second. Magnetic field strength measured at 52 nm. This was a monster CME by any standard. At 8:30 UTC. Amateur astronomer Akiko Tanaka in Japan noticed something extraordinary through her 16-inch telescope. The coma is brightening, it's pulsing. Her observation, shared instantly on social media, was confirmed by professional observatories worldwide. The comet seemed to be responding to the approaching storm, its activity increasing dramatically in the final minutes before impact. Dr. Harold Weaver at Johns Hopkins Applied Physics Laboratory provided real-time commentary for NASA TV. What we're seeing is likely caused by the shockwave preceding the CME. It's compressing the comet's coma, causing rapid heating and sublimation. Think of it as the comet's last gasp before the main event. 8:40 UTC. Radio telescopes detected a sudden burst of emissions from the comet. The Very Large Array in New Mexico recorded signals across multiple frequencies, suggesting intense plasma interactions in the comet's environment. Dr. Timothy Bastian, analyzing the data reported, "We're seeing coherent radio emission, possibly cyclotron, maser emission from electrons spiraling in the magnetic field. This is unprecedented from a comet." At 8:45 UTC, space weather satellites at Earth's L1 point detected the CME passing their position. The measurements were fed instantly to waiting scientists. Dr. Janet Lumen from UC Berkeley's Space Sciences Laboratory announced, CME parameters confirmed. Velocity 2,851 km per second. Proton density 45 particles per cubic centimeter. Magnetic field 54 nanotesla with a strong southward component. Impact in 2 minutes. 8 hours, 46 minutes, and 30 seconds, UTC. The Hubble Space Telescope, given emergency priority for this event, captured the comet in unprecedented detail. The images showed jets of material erupting from at least 7 locations on the nucleus, creating a fountain-like display that would have been spectacular from any angle. The coma had expanded to twice its normal size in just the past hour. 8 hours 47 minutes and 0 seconds. ETC impact. The collision began, not with the plasma itself, but with the shockwave traveling ahead of it. Moving faster than the CME proper, this wall of compressed particles and magnetic fields slammed into the comet's coma at nearly 3,000 kilometers per second. The effect was instantaneous and dramatic. "Oh my God," Dr. Casey Lease exclaimed from the control room at Johns Hopkins. The coma just lit up like a Christmas tree. Across multiple wavelengths, the comet's atmosphere began to glow with an intensity never before recorded. The shockwave compressed and heated the coma to temperatures exceeding 100,000 Kelvin, causing molecules to dissociate and atoms to ionize in a cascade of electromagnetic radiation. Within seconds, the main body of the CME arrived. The impact was visible even in modest telescopes as the comet suddenly brightened by more than 3 magnitudes. Amateur astronomers in Australia and New Zealand, where the comet was visible in the pre-dawn sky, reported seeing it rival Venus in brightness for several minutes. The scientific instruments captured data at a furious pace. Spectroscopes revealed a chemical inventory of the comet being laid bare as layers of ice were stripped away. Dr. Stephanie Millam at NASA Goddard, analyzing the spectra in real time, could barely contain her excitement. "We're seeing species we've never detected before. Complex organics, noble gas compounds, isotopic ratios that are completely alien to our solar system. This is incredible." The magnetic field carried by the CME wrapped around the comet like an invisible cocoon, creating a temporary magnetosphere. This interaction produced something unprecedented: auroras in the comet's coma. The normally invisible magnetic field lines became traced by glowing gases, creating curtains and spirals of light that danced around the nucleus. At 8:52 UTC, 5 minutes after initial impact, the first signs of nuclear fragmentation appeared. The Atacama Large Millimeter Array detected multiple sources of thermal emission where previously there had been one. Dr. Colin Snodgrass at the University of Edinburgh confirmed, "The nucleus is breaking up. We're counting at least 4 major fragments, possibly more. Each piece is becoming an independent comet." The fragmentation was not the gentle splitting astronomers had seen in other comets. This was violent, explosive separation caused by the sudden heating of subsurface ices. As the CME's energy penetrated deep into the nucleus, pockets of supervolatile isis nitrogen, carbon monoxide, methane, creating enormous pressure that literally blew the comet apart. High-speed cameras captured fountain-like geysers of material erupting from the fragmenting nucleus. Some jets reached velocities of over 2 kilometers per second, far exceeding the comet's escape velocity. Dr. Michael Ahern from the University of Maryland, a veteran of the Deep Impact mission, provided perspective. "We deliberately crashed a spacecraft into Comet Tempel 1 to see what was inside. What we're witnessing here is nature doing the same thing, but with 1,000,000 times more energy." The radio emissions intensified dramatically. The Arecibo Observatory's successor facility detected signals reminiscent of Jupiter's radio storms, suggesting intense cyclotron maser emission in the temporary magnetosphere around the comet. Dr. Imke De Potter from UC Berkeley explained, "The CME has essentially turned the comet into a giant particle accelerator. Electrons are being accelerated to near light speed in the magnetic field, producing these incredible radio emissions." At 9 o'clock UTC, 13 minutes after impact, the comet's appearance had transformed completely. What had been a classic comet, with a single nucleus and elegant tail, was now a chaotic cloud of fragments, each trailing its own tail of gas and dust. The combined brightness of all fragments exceeded the original comet by a factor of 10, making it easily visible even in twilight skies. The Parker Solar Probe, though not ideally positioned, managed to detect the interaction from its vantage point closer to the Sun. Dr. Nur Roafi from Johns Hopkins reported, "We're seeing energetic particle enhancements consistent with acceleration at the comet. This comet has become a source of cosmic rays in its own right." Public reaction was immediate and overwhelming. Social media platforms struggled to handle the traffic as millions shared images and videos. #CometExplosion became the top trending topic globally within minutes. News networks scrambled to get expert commentary, with astronomers who had been awake for days suddenly finding themselves explaining complex plasma physics to morning show audiences. At 9:15 UTC, as the initial chaos began to subside, the true scale of the event became clear. The largest fragment, designated 3I at Lissa, was estimated to be about 3 kilometers in diameter. 3 other major fragments, B, C, and D, ranged from 1 to 2 kilometers, with dozens of smaller pieces creating a glittering cloud of debris. Each fragment was active, sublimating furiously in the solar radiation. Dr. Karen Meach from the University of Hawaii's Institute for Astronomy provided crucial context. "What we've witnessed is not destruction, but revelation. Each of these fragments is now exposing pristine material from deep within the original nucleus. We're seeing ices and minerals that have been locked away since before our solar system formed. This is like having multiple interstellar comets to study, instead of just one." The spectroscopic bonanza continued. As each fragment rotated, different faces were exposed to sunlight, revealing compositional variations that told the story of the comet's formation. Isotopic ratios of hydrogen, carbon, nitrogen, and oxygen confirmed the comet's interstellar origin while revealing subtle differences from fragment to fragment, suggesting a complex formation history. At 9:30 UTC, an unexpected phenomenon emerged. The interaction between the CME's magnetic field and the ionized gas around the comet fragments created a series of magnetic reconnection events. These produced X-ray flashes detected by the Chandra X-ray Observatory. Dr. Kerry Leese explained, "We're seeing the same process that creates solar flares, but happening in the comet's temporary magnetosphere. It's like the comet is having its own series of mini-flares." The dust released by the fragmentation began to spread along the comet's orbit, creating what would eventually become a meteor stream. Dr. Peter Jeniskins from the SETI Institute calculated the implications. In about 50 to 100 years, when Earth passes through this debris stream, we'll have meteor showers from another star system. These will be the first truly interstellar meteors observable from Earth. As the first hour after impact concluded, the full magnitude of what had occurred began to sink in. This wasn't just a spectacular celestial event, it was a treasure trove of scientific data that would take years to fully analyze. Graduate students around the world realized their thesis topics had just been decided. Funding agencies began preparing for a flood of grant proposals. The comet that had arrived as a single messenger from another star had become a fleet of ambassadors, each carrying unique information about its distant birthplace. Dr. Alan Stern, principal investigator of the New Horizons mission, summed up the moment. "We've just witnessed one of the most scientifically valuable events in the history of astronomy. The CME has done what no spacecraft could do. It's taken apart an interstellar comet piece by piece, laying bare its secrets for us to study." The data we're collecting right now will revolutionize our understanding of planetary formation, not just in our solar system, but throughout the galaxy. The cosmic collision between solar fury and interstellar ice had exceeded all expectations, transforming a single comet into a complex system of fragments, each telling its own story of cosmic history. As observations continued and data poured in from instruments around the world and in space, one thing was clear: the universe had just provided humanity with one of its greatest teaching moments. Written in fire and ice across the morning sky. Part 4. Aftermath and Revelations, The Legacy of a Cosmic COLOIUSCO in February 15, 2025. 2 weeks had passed since the spectacular collision between Comet 3I Atlas and the coronal mass ejection, and the scientific community was still reeling from the discoveries pouring in. What had begun as a single interstellar visitor had transformed into a complex system of fragments, each revealing new secrets about the cosmos beyond our solar system. Dr. Michael Kelly from the University of Maryland stood before a packed auditorium at the emergency session of the American Astronomical Society. Ladies and gentlemen, what we've learned in the past 2 weeks has fundamentally changed our understanding of interstellar medium composition and comet formation. The data from 3I Atlas is rewriting textbooks in real time. The fragmentation had created an unprecedented opportunity. Each piece of the former comet was exposing different layers of material, like a cosmic archaeology dig revealing strata of history. Fragment A, the largest piece, showed a complex structure with distinct layers of different ices. Fragment B was rich in organic compounds, including amino acids and complex carbon chains. Fragment C contained an unusually high concentration of crystalline silicates, suggesting formation in a warmer environment than expected. Fragment D, perhaps most intriguingly, showed evidence of having been processed by radiation from a different type of star than our Sun. Dr. Stephanie Milam, at NASA Goddard, had been working around the clock analyzing spectroscopic data. Her team's findings were revolutionary. We've identified over 30 molecular species that have never been seen in solar system comets. Most remarkably, we're seeing deuterium to hydrogen ratios that vary between fragments, suggesting this comet assembled from materials that formed in different regions of its parent system, more possibly even from multiple stellar systems. The public engagement with the event had reached unprecedented levels. Amateur astronomers worldwide were tracking the fragments, now spread across several degrees of sky. The brightest pieces remained visible to the naked eye, creating what observers described as a string of pearls in the pre-dawn sky. Astrophotographer Roberto Martinez from Chile captured an image that would grace the covers of magazines worldwide. All 4 major fragments in a single frame, each with its own distinct tail, set against the backdrop of the Milky Way. But the scientific revelations went far beyond pretty pictures. The European Space Agency's Rosetta mission had previously shown how complex comets could be, but 3I Atlas was revealing complexity on another level entirely. Dr. Catherine Oldwig, from the University of Bern, who had worked on Rosetta, explained, Comet 67P, Churyumov of Gerasimenko showed us how complicated our own solar system's comets are, but 3I Atlas is showing us that interstellar comets are archives of not just one stellar system, but potentially multiple generations of stars. The radio emissions detected during the CME impact had opened an entirely new field of study. Dr. Timothy Bastian from the National Radio Astronomy Observatory published preliminary findings showing that the comet fragments continued to emit radio waves days after the impact, suggesting ongoing particle acceleration in the disturbed magnetic environment. We're essentially seeing a natural particle physics experiment. The comet fragments are acting like cosmic accelerators, and we're learning about plasma physics in ways we never imagined. One of the most unexpected discoveries came from analysis of the dust particles released during the fragmentation. Dr. Scott Messenger from NASA's Johnson Space Center, examining particles collected by high-altitude aircraft, made a startling announcement. We've found presolar grains axial stardust that predates our solar system but with isotopic signatures unlike any in our collections. These grains appear to have formed around stars very different from our Sun, possibly including some exotic stellar types we've only theorized about. The biological implications were equally profound. Dr. Zita Martins from Instituto Superior Técnico in Lisbon reported finding complex organic molecules that showed signs of aqueous alteration. These organics didn't just form in cold interstellar space. They've been processed by liquid water, suggesting the parent body of 3I Atlas once harbored subsurface oceans. We're looking at evidence of potentially habitable environments in other stellar systems. As February progressed, the fragment swarm continued to evolve. Each piece was developing its own coma and tail, creating a spectacular display for observers. But more importantly for scientists, each fragment was revealing different aspects of the original comet structure and history. High-resolution radar observations from Arecibo's successor showed that Fragment A had a binary structure. It was actually two pieces held together by weak gravity, suggesting the original comet had a complex, multi-lobed structure. Dr. Alan Fitzsimmons from Queen's University Belfast led a team studying the fragment's orbits. Their calculations revealed something remarkable. The fragments are following slightly different trajectories due to non-gravitational forces, the rocket effect of their outgassing. But here's the amazing part. When we trace these orbits backward, accounting for the CME impact, they don't quite converge at a single point. This suggests 3I Atlas was already a loosely bound collection of cometesimals rather than a single solid body. The implications for planetary formation theories were significant. Dr. Alessandro Morbidelli from the Kate d'Azur Observatory explained, "We're seeing evidence that even in other stellar systems, comets form through gentle accretion of smaller bodies, just as we believe happened in our own solar system. But the composition tells us this accretion happened in an environment very different from our early solar nebula." Public interest showed no signs of waning. Museums reported record attendance for astronomy exhibits. Universities saw surges in applications for astronomy and planetary science programs. Science fiction authors found inspiration in the event, with several announcing novels based on the concept of interstellar messengers. The comet fragments even influenced popular culture, with musicians composing symphonies inspired by the radio, emissions and artists creating installations based on the spectroscopic data. By late February, space agencies were fast-tracking missions to study the fragments. The European Space Agency announced the Interstellar Fragment Explorer, IFE, a spacecraft that would launch in 2027 to rendezvous with Fragment B. NASA proposed the Origins Spectroscopic Survey Observatory, OST, designed to study all the major fragments during their outbound journey. Even private space companies expressed interest, with SpaceX announcing they were studying the feasibility of a sample return mission. Dr. Olivier Hainaut from the European Southern Observatory provided a sobering perspective on the long-term implications. What we've witnessed with 3I Atlas is likely just the beginning. Now that we know what to look for, we're going to find more interstellar visitors. Each one will tell us something new about the galaxy we inhabit. We're entering a new era of galactic archaeology. The data from the CME impact continued to yield surprises. Analysis of the X-ray emissions detected during the collision revealed that some of the comet's assays had been heated to millions of degrees, creating a temporary plasma that mimicked conditions in stellar coronae. Dr. Kathy Reeves from the Harvard-Smithsonian Center for Astrophysics noted, "For a brief moment, the comet became a miniature star, undergoing nuclear processes we normally only see in stellar atmospheres. We detected trace amounts of elements that could only have been created through nuclear reactions during the impact." As March 2025 began, the fragments were starting to fade as they moved away from the Sun. But the scientific analysis was just beginning. Supercomputers worldwide were processing the terabytes of data collected during the encounter. Machine learning algorithms were being deployed to search for patterns and anomalies that human analysts might miss. Every major scientific journal had special issues planned to present the findings. Dr. Lucy Zeres from the University of Arizona Stewart Observatory made a discovery that captured imaginations worldwide. We've detected phosphine and other biomarker molecules in fragment C. While this doesn't mean there's life in other stellar systems, it does show that the chemical precursors to life are common throughout the galaxy. The building blocks are everywhere. It's just a matter of having the right conditions to assemble them. The meteor stream created by the fragmentation was already being modeled in detail. Dr. Peter Janiskins refined his predictions. The debris from 3I Atlas will give us annual meteor showers starting around 2075. But here's the exciting part: because we know the exact composition of the parent body, we'll be able to study interstellar material entering Earth's atmosphere. It will be like having samples from another star system delivered to our doorstep. Educational institutions worldwide incorporated the 3I Atlas event into their curricula. Students from elementary school through graduate programs studied different aspects of the encounter. A generation of young scientists was being inspired by witnessing this cosmic event firsthand. Dr. Neil deGrasse Tyson, commenting on the educational impact, said, "This event has done more to engage the public with astronomy than anything in the past decade. We've shown people that the universe isn't just something to look at, it's something that actively teaches us, if we're ready to learn." As the fragments continued their journey out of the solar system, now forever altered by their encounter with our sun, the scientific community was already looking ahead. The event had demonstrated the value of being prepared for unexpected celestial events. Proposals for dedicated interstellar object survey telescopes gained support. New instruments designed specifically to study fast-moving objects were being designed. Dr. Michelle Bannister from the University of Canterbury in New Zealand offered a philosophical perspective. 3I Atlas has reminded us that we're not isolated in our cosmic neighborhood. Material from other stars passes through our solar system regularly. We're part of a galactic ecosystem where stars exchange material over millions of years. In a very real sense, we've just witnessed our solar system having a conversation with another star system. The legacy of the CME Comet collision would extend far beyond the immediate scientific findings. It had demonstrated the power of international cooperation in astronomy, with data shared freely across borders and time zones. It had shown the value of maintaining diverse observational capabilities, from radio telescopes to spacecraft. Most importantly, it had proven that the universe still held surprises that could unite humanity in wonder and curiosity. As this cosmic drama drew to a close, with the fragments of 3I Atlas fading into the darkness between stars, the impact of their brief, violent transformation continued to ripple through human understanding. Papers would be written, theories would be revised, and new questions would emerge. But perhaps the most lasting legacy would be the reminder that we live in a dynamic, interconnected universe where the gentle ice of distant stars can meet the fury of our sun in a collision that illuminates the cosmos in ways we never imagined. Dr. Martin Rees, Astronomer Royal of the United Kingdom, offered final thoughts that resonated throughout the scientific community. The story of 3I Atlas is far from over. These fragments will continue their journey for millions of years, perhaps one day entering another stellar system where other astronomers might study them and wonder about their origin. We've been privileged to witness a chapter in a story that spans the galaxy, and in studying these messengers from afar, we've learned not just about other stars, but about our own place in the cosmic tapestry. The interstellar comet that had arrived as a single, pristine messenger had departed as a fleet of fragments, each carrying away a piece of our sun's energy while leaving behind a treasure trove of knowledge. The universe had provided humanity with one of its greatest teachers, and we had proven ready to learn. As observers around the world bid farewell to the fading fragments of 3I Atlas, they did so with the knowledge that this encounter had forever changed our understanding of the cosmos and our place within it. Part 5. The Eternal Journey. Legacy of interstellar messaciange. NOS 6 months had passed since the spectacular collision between Comet 3I Atlas and the coronal mass ejection. It was August 2025, and while the fragments had faded from naked eye visibility, Their impact on science and human consciousness continued to reverberate across the globe. The comet, that had arrived as a single messenger from the stars, had become a catalyst for a new era in astronomy and our understanding of our place in the cosmos. Dr. Sarah Chen, the astronomer who had first discovered 3I Atlas, stood before the International Astronomical Union's General Assembly in Cape Town, South Africa. When I first saw that faint smudge of light moving through our detection systems, I never imagined it would transform our field so completely. The legacy of 3I Atlas extends far beyond the scientific papers. Though there have been over 1,200 of those published already, it has fundamentally changed how we view our solar system's relationship with the galaxy. The scientific harvest from the encounter continued to yield remarkable discoveries. Dr. Dante Loretta from the University of Arizona, principal investigator of the OSIRIS-REx mission, presented findings that linked 3I Atlas to the earliest stages of planetary formation. The isotopic anomalies we've documented in the fragments suggest this comet formed in a stellar nursery very different from our own. We're seeing evidence of input from multiple supernovae, possibly including rare events like electron capture, supernova, that produce unique isotopic signatures. The fragments themselves, now designated as separate comets 3I Atlasa through 3I Atlas D, plus dozens of smaller pieces, continued their outward journey. Each fragment was developing its own unique characteristics as different ice compositions drove varying levels of activity. Fragment B, rich in organic compounds, had developed a distinctive green coma from diatomic carbon that persisted even as it passed beyond Mars's orbit. Fragment C exhibited periodic outbursts every 47 hours, suggesting a complex rotation state induced by the violent fragmentation. Dr. Meenakshi Wardwa from Arizona State University revealed groundbreaking analysis of collected dust particles. We've identified mineral phases that require formation temperatures exceeding 1,500 Kelvin, alongside ices that never experienced temperatures above 20 Kelvin. This comet was a mixture of materials from the hottest inner regions and coldest outer regions of its parent system, Moore systems. It's like finding volcanic rock mixed with Antarctic ice, but on a cosmic scale. The public engagement sparked by 3I Atlas had evolved into a sustained interest in astronomy. Observatory visitor numbers remained at record highs. Amateur astronomy equipment sales had increased by 300%. More significantly, science education at all levels had been transformed. Dr. Mae Jemison, former astronaut and science advocate, noted, "We're seeing what educators call a Sputnik moment for the 21st century. Young people who witnessed the CME impact are choosing STEM careers at unprecedented rates. The comet has given us a generation of future scientists." The technological advances, spurred by the need to study 3I Atlas, were already bearing fruit. The extremely large telescope in Chile had fast-tracked new adaptive optic systems that could track rapidly moving objects. Radio telescope arrays had developed new correlation techniques that improved sensitivity by an order of magnitude. Space agencies had accelerated development of rapid response spacecraft that could be launched quickly to intercept future interstellar visitors. Dr. Avi Loeb from Harvard University, who had been a prominent voice in interstellar object research since AMU, reflected on the broader implications. 3I Atlas has shown us that interstellar space is not empty, but filled with wanderers carrying stories from across the galaxy. We estimate that thousands of such objects pass through our solar system each year. Most are too small or too distant to detect with current technology, but that's changing rapidly. The biological implications of the discoveries continued to astound researchers. Dr. Pascal Ehrenfriend from the German Aerospace Center presented evidence that some organic molecules in the fragments showed signs of catalytic activity. We're not saying these comets carry life, but they carry sophisticated molecular machinery that could jumpstart prebiotic chemistry on any suitable world they encounter. Interstellar comets might be the galaxy's way of seeding planetary systems with the ingredients for life. By September 2025, the first detailed models of the fragments' future trajectories were complete. Dr. Marco Micheli from ESA's Space Situational Awareness Program revealed surprising findings. Due to gravitational perturbations during their passage through our solar system, the fragments will follow different paths through interstellar space. In about 100,000 years, they'll be spread across nearly a Each fragment will potentially visit different star systems over the next few million years, carrying with them not just their original interstellar material, but also atoms from our own Sun, added during the CME impact. This realization led to a profound thought. 3I Atlas was not just a messenger from another star, but would become a messenger from our solar system to future stellar systems. The violent encounter with our Sun's CME had made these fragments hybrid objects, part interstellar visitor, part solar system material. They would carry the isotopic signature of our Sun to distant stars. Just as they had brought alien signatures to us, the cultural impact of 3I Atlas extended into unexpected realms. Musicians had composed symphonies based on the radio emissions detected during the CME impact. The Interstellar Symphony by composer Kaya Sariaho premiered at Carnegie Hall. Translating the comet's electromagnetic voice into haunting melodies, visual artists created installations using the spectroscopic data, turning chemical signatures into stunning light displays. Even fashion designers drew inspiration. With cosmic collision patterns appearing on runways in Paris and Milan, Dr. Caroline Porco, former imaging team leader for the Cassini mission, spoke about the philosophical impact. 3I Atlas has done something no space mission could do. It's made the abstract concept of our galactic neighborhood tangible. People now understand that we're not isolated in our little solar system. We're part of a vast dynamic galaxy where material and perhaps information flows between stars over cosmic time. The search for more interstellar objects had intensified dramatically. The Vera Rubin Observatory, with its unprecedented survey capabilities, was detecting candidate objects weekly. Most turned out to be distant solar system objects, but the detection rate of genuine interstellar visitors was climbing. Dr. Maria Jurek from the University of Washington reported, "We've confirmed 7 new interstellar objects since 3I Atlas. None as spectacular, but each unique. We're building a catalog of galactic wanderers that's revealing patterns about our local galactic environment." One of the most intriguing developments came from analysis of the media stream created by 3I Atlas's fragmentation. Dr. Peter Jeniskins had refined models showing that Earth would pass through the debris in 2076, but Mars would encounter it first in 2071. The Mars encounter is particularly exciting because the thin atmosphere means larger particles will reach the surface. Future Mars colonists might be able to collect actual pieces of 3I Atlas interstellar material delivered directly to the Martian surface. The educational legacy of 3I Atlas was formalized with the establishment of the International Interstellar Object Research Institute, headquartered in Hawaii with nodes worldwide. Dr. Karen Meach, appointed as its first director, outlined its mission: "We're creating a permanent infrastructure to study interstellar visitors. This includes dedicated telescopes, rapid response protocols, and international coordination mechanisms. When the next spectacular interstellar comet arrives and we'll be ready." Space missions to the fragments were progressing from concept to hardware. The European Space Agency's Interstellar Fragment Explorer had passed preliminary design review. Its ion propulsion system would allow it to match velocities with Fragment B in 2031. Conducting the first close-up study of interstellar material, NASA's Origins mission would use a novel solar sail designed to chase fragmentation, while the Japanese Space Agency proposed a sample return mission to collect dust from Fragment C's tail. Dr. Ralph McNutt, from Johns Hopkins Applied Physics Laboratory, veteran of numerous outer solar system missions, provided perspective on the challenges. These fragments are moving at over 30 kilometers per second relative to the Sun. That's twice as fast as our fastest spacecraft. Catching them requires not just new technology, but new thinking about trajectory design and mission operations. The astrobiology community had embraced 3I Atlas as a natural experiment in panspermia, the hypothesis that life can spread between stellar systems, Dr. Chandra Wickramasinghe from the Buckingham Center for Astrobiology argued. The discovery of complex organics that survived the CME impact shows that interstellar comets can deliver prebiotic material even under extreme conditions. Over galactic timescales, such delivery could be a significant mechanism for spreading the building blocks of life. As 2025 drew to a close, the fragments of 3I Atlas had passed beyond the orbit of Jupiter, their paths diverging ever more widely. Amateur astronomers with large telescopes could still track Fragment A, now a 15th magnitude object requiring long exposures to detect, but for professional astronomers with access to large telescopes, the fragments remained bright beacons of discovery. Dr. Michael Brown from Caltech, discoverer of numerous outer solar system objects, reflected on how 3I Atlas had changed the field. We used to think of our solar system as a closed box with occasional visitors. Now we understand it's more like a house with open windows. Material flows in and out continuously. 3I Atlas showed us this exchange in dramatic fashion, but it's happening all the time on smaller scales. The interdisciplinary impact was particularly noteworthy. Plasma physicists studying the CME interaction had developed new models applicable to fusion energy research. Chemists analyzing the complex organics had discovered novel molecular structures with potential applications in materials science. Even philosophers had engaged with the implications. With conferences exploring what interstellar visitors meant for humanity's cosmic perspective, Dr. Lisa Kaltoniger from Cornell University spoke about the search for life implications. Every interstellar comet is a messenger that tells us about conditions around other stars. The diversity we're seeing suggests that planetary systems come in varieties we haven't imagined. This gives us hope that life, if it exists elsewhere, might be more common and more diverse than we thought. The story of 3I Atlas had become a standard case study in science communication. Dr. Neil deGrasse Tyson noted, "This event showed us how to share the excitement of discovery in real time with the public. The combination of spectacular visuals, understandable science, and genuine mystery created a perfect storm of public engagement. It's a model for how science should be communicated in the digital age." Looking ahead, astronomers were preparing for the next phase of interstellar object science. Advanced AI systems were being trained to recognize the subtle signatures of interstellar trajectories in survey data. New spectroscopic techniques were being developed to quickly characterize the composition of fast-moving objects. International protocols were established for sharing data and coordinating observations of future interstellar visitors. Dr. Martin Rees offered a cosmic perspective on the legacy of 3I Atlas. In the grand story of the universe, the few months this comet spent in our solar system were less than a blink. But for humanity, it was a transformative moment. We witnessed material from another star system collide with the fury of our own star. And in that collision, we glimpsed the interconnected nature of our galaxy. The fragments now heading back to interstellar space carry with them atoms from our Sun, making them ambassadors from Earth to the stars. As the first anniversary of 3I Atlas's discovery approached, the comet's legacy was secure. It had transformed from a faint smudge in a survey image to a cultural phenomenon that had advanced multiple fields of science, inspired a generation, and fundamentally changed how humanity views its place in the cosmos. The fragments, now eternal wanderers between the stars, would continue their journey for millions of years, carrying their secrets and their stories across the galaxy. Dr. Sarah Chen, reflecting on the year since her discovery, offered final thoughts. "When we look up at the night sky now, we don't just see distant stars. We see a dynamic, interconnected galaxy where messages in the form of ice and rock travel between stellar systems." 3I Atlas taught us that we're not alone, not in the sense of alien civilizations, but in the sense that we're part of a vast cosmic community where stars share their material across the vastness of space. Every interstellar comet is a reminder that we're citizens not just of Earth, not just of the solar system, but of the galaxy itself. The eternal journey of 3I Atlas continued, its fragments spreading ever wider as they returned to the interstellar realm. Behind them, they left a transformed human civilization, one more aware of its cosmic context, more prepared for future visitors, and more united in the shared adventure of understanding our place in the universe. The comet that had arrived as a stranger had departed as a teacher, and its lessons would echo through human culture and science for generations to come. In the end, 3-1 Atlas had shown humanity that the universe itself is the ultimate storyteller, writing its narratives in ice and rock, in light and plasma, in the eternal dance of matter and energy across the cosmos. And for one brief shining moment, we had been privileged to read a chapter of that vast story, written in the language of the stars.